especially with a large class. All right, we haven't seen you since last Thursday. I don't see you quite as often as my Monday, Wednesday, Friday class. If you're still having questions about switching a lab because you had something else change in your schedule or still waiting to get into the class, Angie at that Stat Student Services email is the best place to contact someone, or even go right over there. She's in West Hall in the Stat Department, and she can actually sometimes help you out much better if you go over to see her personally. So 444 West Hall is where you can find Angie, who is manning my wait list every morning, issuing permissions for the drops that went through at night. So if you still have a question regarding that, see Angie. The pre-labs are working. It wasn't just our site. It wasn't all the 1,570 students bringing SiteMaker down. It was some other issue in SiteMaker, certainly. But the pre-labs are now available and working fine as they did their fix yesterday and reload. So I hope you can also see them adequately and go back to them as needed when you start to do your first real homework set and have to make that histogram or boxplot. Watch the 2-minute video on how to do that rather than have to go through a whole bunch of other stuff to remember how that works. So the videos are there. We still will allow you to finish up your pre-lab by tomorrow afternoon, tomorrow evening. The last lab ends at 7. So if you didn't get it done for your lab yesterday because of the difficulties with SiteMaker, we will extend that. Just email your GSI, work out getting that pre-lab one. We just want you to do it so that you're ready to be able to do some of the other things we do in labs and homework. So you get your point if you do it. You get no points if you don't. So complete that, please. All right. The other item that's coming up on Thursday is when you go to your lecture book homework tool, you will start to see a homework there for you on Thursday morning. This is my testing student homework side, but I have the ability to see anything that's hidden, and I have created that first homework. And so once you click on the little pencil thing that says I'm going to start writing that homework, there's 3 questions. And you'll be able to click through those 3 questions and put in your answers. Some of them are multiple choice. Some of them are typing up a little explanation. And one of them is an upload of a graph to get that practice too. The practice homework going up Thursday is practice. I'm putting it under the required heading just so that there are points on it. And then it will be submitted by the Wednesday after at 11 p.m. automatically for you. The GSIs will get it, and they will grade it to go through that process, because we have a few new GSIs this term who haven't done that yet. And then you will see what the graded homework looks like back to you, maybe with some feedback too if you didn't get something right. It is, again, just practice, so if you're not in the class and haven't subscribed yet, that's fine. If you don't do it, that's fine. It's not going to affect your grade, except that it does give you a full practice so that when that first homework really does come up and you're working on it, maybe those little issues or questions you have will be gone by then. So that'll be available. I'll probably give you a little highlight on that again on Thursday. So office hours have also started, but they're pretty quiet right now. But if you do have an issue, if you want to see how virtual sites works with someone that could help you a little bit more on that, come on in, 274 West Hall. Monday through Wednesday, we're there from 9 till 9. Thursday, 9 o'clock in the morning till 5, and Friday just in the morning time, 9 to 12. You're welcome to go to any of the office hours, even though they may not be your GSI's office hours. And instructor office hours are also posted on C-Tools. You can go to myself or Dr. Venable. The first real homework will not be open until January 20th, but the practice one will start this Thursday. They go from Thursday morning, and you've got a week basically to do it. The following Wednesday night at 11 p.m. It'll be automatically submitted for you. We're working through Chapter 2. We actually should finish much of that up today, maybe a couple more slides on Thursday. For Thursday, I'm asking you to read the chapters 3 and 4. They're short chapters, they're reading chapters. There are not really any formulas in those chapters, maybe just one small one. I posted partially complete notes for those 3 and 4. You've got the notes in your binder, and you can look at a few of the answers. I'm going to go through the ones that are missing as a recap of those chapters at the beginning on Thursday, and then I'll put up a clicker practice quiz. 5 points. I'll actually keep those scores just to show you the histogram of them later, but it will be as if it were a little intermediate practice for you to see if you've got those couple ideas from those 2 reading chapters, more concepts on different types of bias, an experiment versus an observational study, and things like that. So try reading through the chapters, or at least just look at the notes that are online. They're on C-Tools under lecture info. Just read through them before Thursday, and then come ready to recap ideas and try out a little practice quiz. So those are my announcements. Questions or comments on anything before we recap our histograms that we ended up with? Question or comment on anything? All right. Then we're going to recall the two types of variables. We're in chapter 2. The two types of variables were what? Categorical or quantitative. And what was the very first graph we looked at that described a quantitative variables distribution? That gave us the values or categories that your variable could take on and how often they occurred, how many. That first graph we looked at had bars, and it was called a bar chart or bar graph. And then we saw the pie graph along with that. And the basic thing for a numerical summary is just summarizing the counts or percentages that fall into each category. We did that for the sleep-deprived status variable. And then we went on to our quantitative variable where we had students say how much hours of sleep they typically get per night. And the quantitative variable to show its distribution. And by distribution, we just mean give me an idea of what the values are that that variable can take on and how often they tend to occur. And the nice picture for the distribution of a quantitative variable was also one with bars, but it wasn't a bar chart. It was called a histogram. And the histogram is what we looked at. We're going to recap that on page 8 of your notes and then move on to start summarizing the data that's quantitative with numbers, numbers such as a mean and a median. And we'll get through at least to standard deviation by the end of today. So page 8, we had our histogram of the amount of sleep for college students. We did a clicker question at the very end where we talked about the shape of that distribution of amount of sleep. We talked about it being approximately symmetric. And another word that would work would be unimodal, one main motor peak. And then some of you did want to select the skewness aspect. It's not perfectly symmetric, a slight skewness to the left, but it's quite slight. I would leave that as a secondary and not the primary thing I would be looking for. This summary here, approximately symmetric, unimodal, centered around 7 hours, most of the values between 4 and 10, and I can kind of picture that histogram back with that description. So this type of description is what you're asked to write out, even by hand, with your histogram that you make for your pre-lab. All right. So let's move to looking at numerical summaries that would be appropriate. Oh, we have one more histogram here, the what if. So you have a response, you've measured for a study, it's quantitative, so you make a histogram. You look at it graphically first, and this is the picture that you get. So this is not unimodal, it's called what? Bimodal. More than one mode or peak, a bimodal distribution. Well, what would it tell you? I certainly see two groups, kind of two subgroups. I see a group of observations, people that had low scores or low values on the response, and another group that had high scores here. So I see a bimodal distribution. I see that there seems to be two subgroups in my data set. And that's one thing I would comment on and want to try to figure out why that occurred. So there appears to be two subgroups. I would not just note that and then go on and start calculating means and standard deviations, because I want to first figure out why. What made these two groups? Investigate why. Maybe it turns out that the lower observations were for the males in your data set, the higher observations for females. Maybe it's the old versus the young, or some other aspect that you measured. Want to try to investigate why. It might be a gender issue, it might be an age issue. It could be a region issue, something else that affects that response and gives you these two subgroups, which is why in a data set we don't just record only the outcome of interest, we record a lot of other variables too. They may not be the main response variable, but they might help to explain features that we see in our response. We might have to control for or account for age or gender in our analyses if we see such a picture like this. So I would want to try to figure out why, so we look at our data set with other variables that have been measured, maybe more demographic, but they might help us to understand what's going on. And then, of course, I wouldn't just leave the data set grouped together after this, because if you calculate a mean, the mean is going to be sort of the balancing point, and that's not really reflecting either group very well. It wouldn't make sense to summarize this data together. I'd rather probably lead to analyzing the data separately by my subgroups from there on out. So we might end up analyzing data separately for the two subgroups. From there on out, or at least include that variable that just gives us that distinction as a variable to help control for that factor. It's important to look at your data first. If a histogram turned out to be like this and I asked you, should you calculate a mean? Well, you can. You can always have a calculator do that for you. SPSS gives you the mean by default with the histogram, so it doesn't even, make you check first. But it would not make sense to report it. It would not be meaningful in this case. All right, a couple of histogram comments are laid out there for you. The bar chart, we usually have a gap between the bars because it separates the different categories. Whereas histograms, there's often one right next to the other, unless, of course, there's a gap and there's no observations there, and then you have an outlier maybe sticking out at the end. How many classes depends. It's a little bit of judgment, but the computers and calculators will do a default kind of algorithm to work out a reasonable number of categories. You can always go in and change that slightly. You don't want too many. If you had too many categories, then you're going to have just a few values in each. It's going to be kind of a flat pancake kind of histogram. If you have too few, then you have everybody in just a couple of classes, and that's not looking like a very good picture of a distribution either. We like to put relative frequency, just another name for proportion or percent, on the y-axis whenever you're comparing observations. If I wanted to compare the histogram for male versus female college students in terms of amount of sleep, I could do that as long as my axes were matching up. Lots of defaults, lots of options, and you get to see that in SPSS a little bit too. All right, last comment here is just that one of the sections talks about dot plots and stem and leaf plots in your textbook. And we're not going to have you do those particular graphs, but some of the examples that are in there do comment on the shape of the resulting distribution. So it's still good to just kind of glance through, but you won't be asked to make those particular types of graphs. A histogram's a good choice overall. The example that you have on page 10, you can try out on your own. That was a one, I think, on an exam in a spring term. It is another histogram of a quantitative variable. See if you can go through and answer those couple questions. The solutions are already posted on C-Tools. I'll be posting lecture notes filled in up until the end drop ad. And so anything I missed, though, also, or skip in class, I will post no matter what. So under lecture info, you can find part 1 of chapter 2 notes already filled in. Let's turn to the numerical summaries for the rest of today. Numerical summary is only appropriate for quantitative data. Even if you had categorical data that you coded, it may not make sense to do any kind of averaging or finding a median there. But it certainly makes sense for a quantitative variable where we saw a reasonably unimodal, homogeneous set of observations. So you've all calculated a mean at some point, and a median perhaps. Measures of center. We're going to have a couple formulas along the way. They're going to be based on data looking like those x's. X1 is the first observation in your data set. X2 is the second one. This is representing your set of data. So n represents the number of items in your data set. It's sometimes called the sample size. And how do you calculate a mean of a set of data? Add them up, divide by the total number, right? The formula for that then would be what? X1, add X2, add all those observations up to the last observation, and divide by the total number that's represented here by n. The symbol for that type of mean, when it's the mean of your sample, which is usually what kind of numbers or data you have. Usually you don't have the entire population of values, but rather just a sample. It's called the sample mean. It's represented by x bar. It's probably a function on one of your calculators where you can put some data in and press that to get the mean. And it's the mean of your sample. We have a different notation if it is the mean of a population. We have a Greek letter mu that represents a population mean. But usually what we're looking at when we're summarizing data is from a sample part of the larger population, not the entire population. Anything calculated on a sample, again, is called a statistic. So that sample mean is easy to find. A shorthand notation would be to use that summation notation. The summation there, that big sigma, just means add them up, add up what's ever after it. And so that's adding up the x's and dividing by the total. The median, how do we find that? The median is the value that's in the middle, but you have to first order your data from smallest to largest. Let's say you had an odd number of observations, 5 of them. Then there is, if you order them, a middle value, and that would be your median. What if you have only an even number of observations, say 4? So the median is going to be right here. Any value that's between those two numbers could be the median. It would divide your data set into 50% above and 50% below. But in this case, we define it to be the average of those two middle numbers, so we all get the same answer. So the median when n is an odd number of observations, the median, or m, is going to be the middle observation, because there is a unique one. Maybe the same value as some on the either side, but it will be the middle value. Whereas if your number of observations is even, then you're going to define the median to be the average of the two middle observations. All right, let's try it out. We've got our small set of data from that study where students were looking at whether you're getting the same amount of French fries in your small orders. We have the data provided for you there. Again, the note right here is whenever you have quantitative data, the first step should be not calculate a mean and some standard deviation or something like that, but to graph it. Appropriate graph for histogram to show the distribution, to show the values that are possible, is a histogram for quantitative variable. I say we have sort of a unimodal, bell-shaped picture again, roughly symmetric. They range from the 60s up to the lower 80s, and it's centered around the mid to lower 70s. So there's our histogram. It makes sense to calculate a mean to summarize this data. We have some variability there, but it is somewhat homogeneous. So let's calculate that mean first. How would we do it? And what would it be represented by? The symbol would be x bar. We'd have to plug into our calculator or computer this data set, add up all 12 observations and divide by 12. Now, if you have a calculator, I rarely ask you to calculate a mean on this exam. I know you can do it. You can do it with a computer or a calculator. I usually give you some basic summary measures. If we were to calculate this, would a value like 82 even make sense? Right? 82 would be way over here. Is that the balancing point of this? Does that look like the mean? So you want to just make sure that any calculation you do, if you take it back to the picture you've got, that it makes somewhat sense with that picture. 82 would not make sense. 69 may not start to make sense either, but how about more in the middle? A 73.6. And the units here are always good to include whenever you're reporting some numerical summaries, and the units here are the weight in grams. 73.6 is visually about that balancing point. It makes sense with my histogram. We have had pictures of a histogram where we ask you to pick what you think might be the mean and maybe which one might be the median. And you should be able to kind of visualize that but not have to calculate it just from the histogram, but know how it would relate back. All right, how about the median? Median, you need the data in order, and I provided that for you. We have 12 observations. So the median is going to fall in the middle between that 72 and that 74. So the median here will be what? 73. It'll be the average of the two middle observations, 73 grams. Now the mean was 73.6 and the median was 73. The fact that those are kind of similar, does that make sense here too? If you had a roughly symmetric distribution, then the mean and the median would be very close to one another, and that supports it also. All right, well, we have a couple of what ifs there on the bottom. What if we had put the data in our calculator quickly, and instead of putting the 63 in, we actually just put in a 3. So our smallest observation was a 63. What if we had accidentally just typed in the 3 only? How would that affect my measures of center here that we just calculated? How about the median? Would the median change at all? No. The median doesn't use all the values. It uses them in the terms of their place, in terms of their size or order, but it doesn't use every value in the data set. So the median is not going to be affected at all. The median will stay the same. How about the mean? It will change. The mean uses every value. That 3 would enter in instead of a 63 as part of the total on the top. The mean is going to do what, do you think? Go up, go down? It's going to go down. That one smaller value, being smaller yet, is going to drag that mean down. In fact, the mean would decrease. The mean would decrease to 68.6. There would only be a couple observations below the mean, 10 of them above it. Much different than what we had before. So the mean would be smaller. So we talk about the mean is affected by extreme observations. The median is not so. It is more of a resistant measure. Top of the next page, let's fill that idea in. The mean is sensitive to extreme observations, whereas the median is our more resistant measure of center. So which measure of center might be the better one to report if in looking at your histogram it was strongly skewed, maybe with a couple of outliers, either on the high or low end? The median. The median would paint a better picture of what really is more of the middle observation, where more of the typical values tend to be, rather than the mean. The mean can be affected by those extreme observations. Very good. All right, a couple pictures to show the relationship between the mean and the median. What is the descriptor of this first one again? We call this bell-shaped, symmetric, unimodal. All of those words would work. And the symmetry is the main idea here. How will the mean and median compare? And where will they be? Both right in the middle and approximately equal to each other. The smoothed out histogram being shown on the right, upper right, that is also symmetric. What's the other word to describe this one? Uniform. Not unimodal, but uniform. It actually doesn't have really any mode, or they're all modes, if you will, because they're all equally likely. Symmetric, uniform, it's still symmetric. So it would be quite easy here to also find the mean and the median. You just need to find the midpoint. So if I gave you the endpoints, you would be able to find the mean and median for that one, even without having more detail of how many observations and all the individual values. All right, we've got two skewed distributions. This first one here is again what? Skewed to the right. Look at where the tail ends up being pulled out. Skewed to the right. That is more for income data, sales of homes, that type. And skewed to the right means we've got a lot of values that are small, and then we're throwing in a few really large values into that data set and averaging. So the mean and median are not going to be the same. Which one would tend to be higher? You've got a bunch of 1s, 2s, and 3s, and you throw in a couple of really large numbers. It's going to pull the mean towards those large values. All right, skewed to the right. Relative to each other, the median would be the smaller one and be less than the mean. Exactly how much smaller, exactly where they're placed. Median is going to be the value on the axes, so that if you looked at the area to the right and left, it should be both about 50%, because the median divides things in half that way. The mean should be more visually the balancing point of that histogram or that smooth curve. But relative to each other, that's how they should compare. The mean gets pulled in direction of the tail. Our other distribution here is skewed to the left. Very typical of your exam scores in this class. The mean and median, again, will not be equal to each other, but it'll be the mean that gets pulled down compared to the median in this distribution, which is why I often report the 5-number summary, or the median, as far as my measure of center when I report scores on your exams, rather than the mean. The mean can get pulled down by that 1 or 2 or few low scores that end up happening. And what's the descriptor for our last graph there? Bimodal. 2 main modes are peak. It's still a roughly symmetric. And where would the mean and median be there? Kind of in the middle again. Does either one of those measures of center really represent what we think of as the center as being that sort of typical value? Not very well. So neither does a very good job as a summary measure here. One of the old exams had a picture that ended up being somewhat bimodal, showing distinct clusters. And the question was, should you report the mean here for this quantitative variable? Is that an appropriate measure? If yes, go ahead and report it, and it was right in the output summary. If no, explain why not. And for that type of picture, I would say no. And the reason is that you seem to have 2 subgroups, and you shouldn't be aggregating them, combining them together. All right, there's measures of center. Mean and median are the typical ones. We know when it's appropriate to use either one, and when it's appropriate perhaps to use one over the other. Median preferred when it's skewed or strong outliers in your data set. Measures of center are done. Measures of spread come next. So what if you had the distribution of scores on an exam that were somewhat unimodal, bell-shaped symmetric, and the mean was reported to be 76, and you scored an 88? How do you feel? Good? You're above the mean at least, right? How good should you feel? Let's suppose 76 is our mean there and 88 is right about here. So there's one model. Would you feel better with the distribution of scores looking like that, number 1 or number 2? Number 2, right? Number 2, relative to the peers in the scores, you're looking much better compared to the first distribution. They both have the same shape, they both have the same center, but they differ in their spread or variation. And it's important to know that aspect of your model too. And a score from one distribution being 88 from 76 may look better relative to that idea of how spread out the values are. So a couple measures of spread to go along with measures of center. The two easiest ones, of course, or the easiest one that is the range. Just look at the overall range of your data set. The range is defined to be the max minus the min. So if I have you calculate the range, I want you to take the largest value and subtract the smallest one off and get that spread of that 100% of your data. If I ask you to just comment on spread, one comment you can make is it goes from 10 to 22. And that's kind of giving me the range, but it's not computing it. Another way of giving you some idea of the breakdown is to report some percentiles. In fact, a lot of your standardized tests report your score and what percentile you got. In the two pictures we just looked at, you would have a higher percentile when there was less spread in your model. So percentiles tell you a value so that you know what percent are below it and what percent therefore are above it. Common percentiles, we've already done one of them. The median is actually a percentile of your distribution. It is the 50th percentile because it cuts your data set in half, half below, half above. If you were to take the lower half of your data set, below the median, and pretend that's your data set and find the median again, that would be what is called the first quartile or the 25th percentile. And the first quartile is denoted typically with a Q1. If you were to take your data set, find the median and take all the values above the median, find the median of that set again, you'd have the upper quartile or Q3 or third quartile, also known as the 75th percentile. So it's just dividing each half of the data set in half again. And those two quartiles then give you another little bit of positional idea in your data set. If you take those numbers, the median, the quartiles, along with the min and the max, and put them in a table, this is the way your textbook lays out this summary. It's called the 5-number summary. It gives you all in one kind of picture here, a couple measures of spread. One measure of spread would be the max minus the min, so you get the range by looking at that distance. You get the median as your measure of center, and then another measure of spread that's sometimes used instead of the overall range is called the interquartile range, or IQR. Interquartile range. It's the measure of the spread for the middle 50% of your data, because the range depends on your two most extreme values. What if one of those values is an outlier? So your range looks distorted to be quite large when most of your data is really in this range instead, a smaller range. IQR, interquartile range. So nice set of summaries for when you have skewed data or outliers would be a 5-number summary. It gives you center and spread in a couple of ways. Let's try it out. Our French fry data set again. Why don't you go ahead and try to work out the 5-number summary. We found the median already. Min and max are easy to put in. And then let's find those quartiles. So 12 observations. Middle. So I'm finding Q1 and Q3. Not too bad here, right? You just take your data that's below and above that median position. What is going to be Q3? I need these lower observations. There's 6 of them down there. So the middle falls right here now between the 69 and the 70. So Q1, the lower quartile, will be what? 69.5. And on the upper side, there's another 6 observations in that upper half. And finding the middle there would be Q3, 78.5. All right, so the range is easily found. The actual computation of the range would be the maximum value minus the min. The overall range of the data covers 20 grams for a spread. The interquartile range, defined again to be Q3 minus Q1. Looking at the spread of the middle 50% of your data would be that 78.5 minus the 69. 69.5. A difference there of only 9 grams instead. So the middle 50% cover a range of 9 grams. You can compare from one data set to another the common measures, such as IQR, to see which one looks like it's more spread out in terms of that middle 50%. Now a quick what if here. What if that 83 were not there? So instead of having 12 observations, I have 11. So now what will be my median of this data set? The 72. And looking at finding Q1 and Q3, what would I do? So now I'm looking at just the 5 observations below the 72. I'm not going to include the 72 in that lower half. So the definition of Q1 when you have a median being one of the values in your data set is everything strictly below and strictly above. That works for both an odd and an even. So then my Q1 would have been a 69, and looking at only the 5 observations above, my Q3 would have been the 78. Just so you know how the calculators and computers are doing, that's typically the method of using it. Sometimes they specifically take 0.25 times the sample size to find the position of that 25th observation or 25th percentile and even interpolate. But this is the method that most calculators and computers use. All right. The test score example is another one that you can try out on your own. It's really not too difficult to work through. You just report values from that 5-number summary. It's very similar to one of the examples in Chapter 1, which I asked you to read initially, and it went through a 5-number summary there and pulling out a few values. So try that one out. That will be posted up on CTools very soon. We're going to look at another graph today called Boxplots. You probably saw that in your pre-lab if you looked at your pre-lab video, or maybe even saw one in lab. It is a picture of your 5-number summary in graphical form. So you take your 5-number summary. You take your quartiles, Q1 and Q3, and you use those to form your box. The length of the box is your IQR visually. So Q1 and Q3, so this length here is really your interquartile range. It's visually showing you that spread of the middle 50% of your data. Inside the box, wherever it occurs, you put your median with a line drawn in the middle of the box. Now here it's shown more in the middle. It could be that your Q1 and your median are the same. If you had a lot of repeats in your data set, it's possible, so there might not even be a line in the middle of the box. And then you do a little check. You check to see if there's any outliers, because if there's outliers, I want to still show them visually in the graph that we're making here. There's a rule for checking for outliers. It's called the 1.5 times IQR rule, because you calculate 1.5 times IQR. And that quantities your step, your amount that you go out from the quartiles. You take Q1 and you go down 1 step. You take Q3 and you go up 1 step. And those values are your fences or your boundaries. Turns out, with a little bit of theory, you can show that any values that are outside those fences are unusual. They would be deemed an outlier using this rule. So you take 1.5 times the IQR, you go out a step from your quartiles, put like little boundaries there, fences, and say, do I have any observations that are outside those fences? If I do, I want to plot them separately and draw attention to them because they're sticking out from the rest. If I don't, then just extend the lines out to the actual min and max because there were no outliers in that data set. So you plot them individually if you have any. If not, just extend them out to the smallest and largest observation. If there are outliers, you say, apart from those outliers, what are the min and max? And draw your box plot accordingly. So this box plot right here is for your 12 orders of French fries, their weights. I do not see any points plotted outside the length of those boxes, those whiskers going out individually. I didn't have any outliers in this example. If you remember the histogram that we looked at a little bit ago, it didn't have any outliers either for this set of 12 observations. So I see no outliers on either end here. They would be plotted separately. I don't see any outliers, so what we're going to do is confirm that there aren't any outliers, trying out this rule once, and then pretend that we do have one larger value and see how that affects the box plot overall. Box plots are going to be made for you typically, and I just want you to know how they're constructed. So let's do one little check on how that rule works. What we're doing basically is verifying that there are no outliers in our data set. We didn't see it visually in the histogram. The box plot we just saw there didn't show it. So let's see what that rule is that shows us there aren't any outliers. The interquartile range is the first thing to compute, and that was a difference of 9 grams. We just did that together a minute ago. Calculate that thing called a step. 1.5 times the IQR. So this is my step amount, 13.5. 13.5 is not put on my actual box plot anywhere. It's just the amount I'm going to go out from the quartiles to figure out where these fences can be drawn or thought through. So the lower boundary of fence is taking Q1 and subtracting 1 step. So go from 69.5, which is Q1, subtract off 1 step amount, and come up with your lower boundary, which is a 56. Now that's not necessarily going to be a value in your data set, but you're going to ask yourself, in my data set, did I have any values that were even smaller than that lower boundary? Any observations that fell below 56? What was our lowest value? 63. So we have no outliers on the low side. Any observations that fall below this lower boundary? No. So there are no low outliers. If my lowest value was a 55 or 54, that would start to be deemed an outlier, and I'd be plotting that separately. But there is no outlier on the low end. The 56 didn't appear on my box plot that you had at the top of that page, but that is the boundary that I'm using to determine if there would be a point I'd plot separately. What about on the upper end? The upper boundary or fence is 78.5, going up 1 step. Gives us a boundary of 92. Again, you may or may not even have that value in your data set, but you're going to be asking, do I have any values that go beyond that number? Any values on the high end, above 92? Our largest value was 83. So the answer here is also no. So there are no high outliers or large outliers. So we just confirmed the graph that we just made was the graph using that rule, just that it didn't have any outliers, so we just drew the lines out to the min and max. What would happen if there were an outlier? How does the box plot change? So we're going to pretend on the next page that that largest value of 83 is really a 93. So we will have an outlier and see how the graph changes. So if we change from 83 to 93, just makes the one large value a bit larger. Does the median change? Is the median affected by those extreme kind of values? No, still 73. In fact, the quartiles are going to be the same too. We're just shifting that one large value out there further, so it's still going to be the same Q1 and Q3. Everything's the same except for the largest value, which is a 93 now. The boundaries that we computed on the previous slide, that 56 lower boundary and that 92 still stand as the boundaries to determine if we have outliers. But now on the high side, 92's out there and I have a 93. It goes beyond. So now I do have one high outlier, the value of my 93. That's the point that's plotted separately here. Different symbols used depending on the package. It might be dots or asterisks, but any point that's plotted separately is an outlier by this rule. There actually could have been, without knowing the data set, at least one outlier here, because there could be two values at that same high value. But we plot that separately, and then The lower box whisker goes out to still the 63 because we didn't have any low outliers. That upper whisker or line goes up to an 80. Notice that this doesn't go up to the 92, which was our boundary, because we didn't have any values at 92. That was just used to determine if we have an outlier or not. The upper end here should go up to the largest value in our data set that's not an outlier, which we would have plotted separately. And our largest value that's not an outlier is 80. Why does the line extend out to 80? It's the largest value that is not an outlier. The lower boundary of 56 and the upper boundary of 92 don't appear on the graph. They are sort of your invisible fences. Got one kind of fence right there and one way down over here, just to determine which values, if there are any, would be plotted separately. So now I can see truly where most of the values are. I see the outlier plotted separately. I see the gap, which I would have seen in the histogram too. If you have the histogram and just that one larger outcome was moved way out larger, you would have had a gap of values and seen that outlier through the histogram, but also drawn to your attention in the box plot. All right, so the box plots are going to be made for you. I don't like to have you work out this IQR rule by hand and try to draw them out, but know what these values are that are plotted separately and how they came to be plotted that way. A couple notes then to fill in. Box plots are very helpful when you want to make comparisons. You can make side-by-side box plots, one box plot for males, one for females, to compare the two distributions quite easily. So side-by-side box plots are good for comparing two or more sets of observations. It automatically puts them on the same axes, the same scaling, so that you don't have to go in and click the axes and make the two histograms have the same x and y axes scaling, so you can compare them, puts them right next to each other. We'll do that quite often for a visual check when we look at multiple comparisons for different groups. Watching out for those points that are plotted separately. They're called what again? They're outliers. And my point here is that they are still part of the data set. I don't want you to ignore them. In fact, they were plotted there separately, so you would be drawn to see them. Maybe that outlier is the most interesting observation in your data set. Here's all the data, and that observation is really good. How did we get to be that good for that combination of factors that I put together? I might want to focus on that one rather than the rest. All right, so they're still part of the data set. Don't ignore them. They're there to show you that they did stand out from the general rest of the data set. One thing that box plots do not do very well, that we can't see from a box plot alone very well, is shape. You can't confirm shape from a box plot only. What graph does a much better job of showing us the shape of the distribution of our quantitative variable? A histogram. Your box plot can look beautifully symmetric, but your data set underlying it may not be. Just because your median is right in the middle to Q1 and Q3, you don't know what happens in between Q1 and the median and Q3. How are the data distributed that way? They could be all clumped to one end and then clumped to the middle on the other side, so it may not have that same pattern that you're thinking that the box plot tends to show. So it doesn't confirm shape. You can start to see skewness. A box plot showing some skewness would be a long tail going out and a bunch of outliers on one end, so you could start to see or visualize that, but it still doesn't confirm the shape. We'd want to use a histogram instead. And then one other graph you're going to look at in labs number 2. No labs next week, remember, because there's no Monday classes, so we don't hold labs at all for next week. But the second lab, you're going to look at QQ plots. That'll show you whether you have a bell-shaped model in a better way. You're going to look at time plots, because a lot of data we gather are over time. So a couple more graphs that we'll look at. And then my last comment really helps you on an exam or a quiz if we were to give one, and that is that show me what you're doing when you're reading values off the graph. If you're looking all over and reading that value that was the outlier as a 92 instead of 93, well, I might give you credit for something that's reasonable based on where the axes are and how fine they are for you to read values from. Show me what you're doing so I can see your approach and still give you credit for the right process. All right, so on the next, oh, I got my comic of the day. Recycling, go green, aluminum cans, bottles. Cycle those boxes. Yeah, okay. What I have next for you is to try out a question that was on an exam in the past. We have here scores on a standardized test for children, and some of those children ate breakfast, some of them did not. So we have their scores compared side by side box plots. So I'm going to ask you to review the notes on that page 16 that we just went through. We'll keep them in mind anyway. Work with a neighbor. Try out these 3 questions, and we will click them in. I'm going to give you some choices then for the actual answers. But try them out, and we'll see how you do. This is a chance for you to talk with your neighbor and work out a problem. So this question that you have was on an exam before, but not with multiple choice on the exam. If your answer is not exactly there, it's probably close to one of those answers perhaps. Pick the closest one. Do you notice in the questions there are sometimes words that are bold or italicized? That usually means they're important to help you guide to the right box plot? We're asking here for the approximate lowest score or grade for a child who does have breakfast. So I want, do you have breakfast? Yes. That's the box plot I want to work with. Looking pretty good. Here's your distribution. Most of you indeed are picking the right answer, which is B, 4.5. Plus 5 points, minus 10 over here. All right. The lowest value, 4.5, is this value right here. What is that called? That's an outlier. But is it still part of the data set? It's the lowest value. There could have been even 2 children that had 4.5, but it is the minimum. If you ignored the outliers, yes, then the next smallest observation is 6. But 6 is not the minimum value here for that data set. And of course, the other answer of 4 was for the other group in case you went to the wrong box plot. Highlighting that. Now, if someone wrote, and I saw someone in one of my other classes wrote 4.6, I would have given credit for that because that's close to what I have there. You know, it is pretty much right in the middle, but if you read it off as 4.4, 4.6, you'd still credit, especially if you were to circle it or bring it over and kind of tell me what you think that number is on the axes. All right, I'm a little more curious about this next question, and go ahead. Among children who did not eat breakfast, 25% had a score of at least how many points? We're a little more split on this one for our question 2. All right, let's take a look. You want to change your answer? Question 2, I see a 25%, so I'm sort of thinking a quartile rather than the median. So the choice over these 3, let's take a look. I'm going to tell you right up front that the right answer is A. Let's see why. All right, we're looking at which box plot? The one with the children that did not eat breakfast, so the no group. I do see what? What is the median for this one? About 6.5. That would be my median. And my quartiles are about this 5.5 and then about 7.5. And I see a 25%, but 25% does not necessarily mean it's going to be Q1. When you take Q1, you've got 25% below. And what percent above? Q1, 75. When you take Q3, you've got another 75-25 split. There's 25% above it and 75% below it. So depending on which quartile you used, depends on which direction you were looking to go for that 25%. So often on these kind of questions, it's almost easier to just say, I know it's a Q1 or Q3, because it could be kind of tricky that way. Put each one in and see if it makes the sentence correct. So let's try the one that was the most common answer. Most of you took 25% and said, oh, it's Q1, 5.5. So what if we put 5.5 in our sentence here? It says, you're looking at the percent of students that had a score of at least 5.5 points. So at least 5.5 points means 5.5 points or more. And what percent of the students had a score of 5.5 points or more? At least 5.5 points. 75%, not 25%. There are 75% that had a score of at least 5.5 points. Let's put in the other Q3 of 7.5. We put in 7.5 and say, what percent of the students had a score of at least 7.5 points? At least means that many points or more. And what percent are there? 25%. The correct answer is A. If it were at most instead of at least. If I had at most there, then you'd be talking about that many points or less, and then you do want 25%, so that's Q1. So is it at least or at most? Is it more than or less than? And you want the 25% in that spot or the 75% tells you which one you use. So you just have to think it through a little bit or kind of try out both numbers and see which one ends up making it correct, noting the direction you're going and what percent you want there in that direction. All right. So that one I put there specifically because that was one on a quiz, I think for a spring term, and I did have the number get it wrong. I'm doing it now so you won't get it wrong if it were asked similarly on your exam. Our last one is a true-false. Let's see what you choose there. We have a very nice symmetric box plot for our not eating breakfast group. The statement is that this implies the distribution for scores is that nice bell-shaped symmetric distribution. No outliers in that one. And most of you paid attention to the notes on the previous page. Notes on the previous page would lead you to say this is false. It is false. Does not imply the distribution is bell-shaped, just because the distribution is symmetric. A symmetric box plot does not necessarily guarantee that your data, when you plot it, will be symmetric. It tells you that your median and your Qs, your Q1 and Q3, are nice and symmetric from each other. And even if you went out to max and min, it'd be the same distance. But what happens in between to that 25% chunks that you've got? They could be distributed in different ways that are not mirrored or symmetric. And even if it were symmetric, does it mean it's going to be this type of symmetry, bell-shaped? Isn't there other symmetry models? Bimodal will give you a symmetric box plot, just the same as a unimodal bell-shaped curve will give you a symmetric box plot. So you can't see the clusters. You can't see bimodality from your box plot. It hides that aspect of shape. Box plots hide clusters and gaps. You don't see them as readily. So shape is not best to imply from any box plot. Look at the histogram along with it. So false. All right. Now we did have one outlier, at least one outlier in our data set. There could actually be 2 children or more there at that low value. What do you do with outliers? A small section in your text, section 2.6, talks about how to handle them. Gives you a couple of good examples for you to look at. The primary idea is that you just can't throw them out and say, oh, they don't match, let's just not use them. You have to take a look at your data. It might be a legitimate value. It might represent something that's been gathered under different conditions. Joe did the measuring of these parts, knew how to operate this machine. Jim came in while he went out to the bathroom and did a measurement and it was way wrong. And that would indicate that you shouldn't use it because it wasn't calibrated correctly or whatever. It could just be natural variability and you occasionally get a value that stands out. But more than likely it could be that someone else made the measurement was entered incorrectly, you go back and check your records. It's just a switching around of the values or something. But it can't throw it out unless there's a legitimate reason to say it doesn't fit with the rest of the data for this situation. It's measured by a different person or on a different machine or under a different condition. It could be that it's an interesting value to look at, and that might be your focus. It could be that that particular person or item belongs to a different group. That was the only male in your data set and everybody else that you asked the question of were all females. So that could give you a different rating or response. All right, so some good examples there. We have techniques that are more resistant to outliers than others. We have a median that's better to report than a mean if there were an outlier. Question in the back? Or just stretching? All right, one last measure of spread, standard deviation, and we end with our pictures of the day. So how many of you have heard of standard deviation, too, as another numerical summary? How it's calculated, how you interpret it will be our last focus. So if you have the median as your measure of center, then you're most likely going to report the range or the IQR, the interquartile range, to go along with it. If you have the mean as a reasonable measure of center, then often you see next to that is the standard deviation as a measure of spread. Because what does the standard deviation do? It measures the spread of your observations from the mean. The standard deviation takes every value in your data set and looks at how far away every observation is from the mean. We're going to interpret the standard deviation in the following way. we want to interpret it as being roughly the average distance that your values are from the mean. It's that typical distance, that average distance of the values from the mean. Now, it's not exactly the average. If you were going to calculate the average, you'd have a little different formula than what we're going to write up here. But it does take distances from the mean, and we want to interpret it or view it as being roughly that average distance. So it can be kind of a yardstick for us to see how far away we are from the mean. So here's how it's computed. Let's work that out. We're going to take every observation and look at how far away it is from the mean. So the first observation would be x1. And what was the mean of a sample again? We represent that by x bar. That represents the sample mean of your set of data. So there's the first distance. And I'm going to calculate the next distance, my next observation from the mean. And I'm going to do that for all of the observations. Every single value is used in calculating the standard deviation, just as it is for calculating the mean. And if I were to average these, I would be starting to add them up then, right? Average these distances. And if you did that calculation right there, that would always come out to be 0. Because some of those distances are positive. Some values were above the mean and some were below the mean. And so every negative and positive ends up, when you work them all out as a total, to add up to 0. That's a property of the mean. The total of the distances of every value from the mean is 0. So you can't really just average that because you'd always get 0. So what's one way of getting rid of the negatives versus positives is to take absolute value, and that would work. That would be called the mean absolute deviation, which is a measure of spread, which really is more of that average distance idea, but it doesn't work very well mathematically. Trying to integrate or show properties of this kind of measurement here, the statistic, when there's absolute values to work with, not so fun. So another way to get rid of it is to square everything. Then a value that's 2 below the mean contributes 4, just as a value that sits 2 above the mean contributes the same distance of 4. But it's in squared units now. So if I were to do squares, I would average those squares by doing what? Add all those square distances up and divide by n. We're going to divide by n minus 1. n minus 1. Sometimes going to be called later for us the degrees of freedom. Those quantities that were in the top numerator there. And before we put the squares there, we said they added up to 0. So if you had 10 numbers, and you know that the distances add up to 0, 9 of those numbers could be anything, giving you any of the distances at all. That last one, though, has to be fixed because it has to make that total add up to 0. So there are 10 observations, but only 9 that are free to vary and be whatever they want to be. That last one's fixed by this constraint because we're looking at distance from the mean. It also turns out that if you do an n minus 1 on the bottom, you're going to get a better estimate out from your data for what the true standard deviation would be for the population than if you didn't correct for that losing of 1 degree of freedom. So later it's going to be called degrees of freedom when we do some inference using this as our measure of spread. Right now we have looking at roughly the average of the squared deviations of the values from the mean, and I don't want to have a measurement in squared units when it comes out. So we take the square root of that whole thing, and you've got the standard deviation. Represented by that little letter s for a sample standard deviation. S goes along with x bar. Those are the symbols for a sample standard deviation. The shorthand notation that's on your yellow card, this is your second formula there, I think the mean is listed there too, would be that you take the sum of the x minus the x bars and square them, dividing that total or sum by that n minus 1. So that's just that more compact notation. You very likely have on your calculator an S button too. Or when you have it do some basic summaries, it will give you that standard deviation, which is nice. What we calculated before we took the square root is called S squared. That's your variance. Variance is not in original units. Variance is in squared units, so we want to bring it back to the original units to be my yardstick. Here's the average and my give or take, my standard deviation each way. So that's how it's computed. Let's try it out once. There's an example in the bottom that you can look at on your own. We're going to calculate it once, but mostly focus on the interpretations that we have in the middle of that next page, page 19. This is probably the only time you're going to calculate the standard deviation by hand, working it out. The rest of the time I want you to use the calculator, or I provide it on the exam for you to interpret. These are our observations. The average was 73.6. That was our x bar. The standard deviation, or S, for our sample. We're going to need a very large square root. We're going to have to start calculating distances of each of the values from their mean. So the first one's a 77 minus the 73.6. And I do have to square that. We're kind of cheating a little bit here and putting in the first and the last observation to show what it would be that you would have to work out and do. With only a very basic calculator, this would take a bit of time, especially with a mean of 73.6, decimal form like that. But I would do all of those squared terms and add them up. So an observation that's further away from the mean contributes more, leading to a higher spread or more variation than if you have a lot of observations that are close to the mean. What will we divide by here? 12 is our observation number, so 12 minus 1. Under the square root, you would get a 35.4. 35.4 has what name again? It's called the variance. It's called the variance. So sometimes you'll see reports that show the variance and the standard deviation. Standard deviation is preferred because we bring it back to original units, and that would be about 5.9. And so we could say the standard deviation is 5.9 grams versus a variance of 35.4 grams squared. Hard to think of squared units. So there's our standard deviation. If you looked at the histogram, the values did vary from the mean. Some of them were more than 5.9 away. Some of them were closer than 5.9 away. But the average distance could be thought of as being about 5.9 grams. Probably the more important thing is to know what this number tells you in terms of an interpretation or viewing it. And then also, when you have certain shapes of distributions, it's very useful for a yardstick, as we will see, not today, on Thursday. So, interpretation's coming first. This is going to be an important page. You're definitely going to have on real homework number 1 somewhere interpreting a standard deviation. I think in one of your modules, it might even be in module 1, there's some good examples to look at if you didn't get to them in lab that were wrong interpretations and right ones, and picking out the right ones. The weights of our small orders of French fries, they weren't all the same. They did vary. They are about how far away from their mean, roughly how far on average. So these weights of small orders of French fries are roughly about 5.9 grams away from their mean, which happened to be the 73.6. And then we've got that important clarifier there, on average. I'm not saying that every order of French fries had the weight that was exactly 5.9 away from the mean. There were some that were farther away, some that were closer, and if you looked at the average of those distances, it'd be about 5.9. So some key parts here is that we are clarifying it because we didn't calculate the absolute values. We did square things and then took the square root. We are talking about an average distance. And I give you the frame of reference from which you're looking at the values from what? From their mean. Another way to write it correctly is start out with the on average. So on average, these weights did vary by about how much from their mean? By about 5.9 grams from their mean, which happens to be known here as 73.6. So there's a couple examples of where you have all the right parts for an interpretation. The standard deviation is thought of as being roughly an average distance. The average distance that the values vary from what frame of reference? From the mean. A data set that had a standard deviation of 5.9 compared to a data set that had a standard deviation of 59, much more spread from the mean on average compared to the other one. All right, standard deviation. Couple notes. Well, how would we get a standard deviation of 0? What would it mean? There's no variation, no spread. Has to occur when all the values are the same. So S could be 0. That's the smallest it could be. It represents that there's no spread at all, no variation. And it would occur, of course, when all the observations are the same. Otherwise, what kind of values do you get for an S, a standard deviation? They have to be positive. Can't get an S of negative 2.8. It would be marked really wrong on the exam. The larger the value, the more spread. The closer to 0, the more consistent the values are and close to the mean on average. Now, the mean was our measure of spread or measure of center that we talked about, was somewhat sensitive to those extreme observations. An extreme observation can pull the mean quite down or up. And the standard deviation looks at every value from that mean. So the standard deviation is also sensitive to extreme observations. So when do we prefer to use the mean and the standard deviation to go along with a graph to show or summarize a quantitative variable? We do that when our distribution looks to be reasonably symmetric and bell-shaped. If our distribution overall looks reasonably symmetric, unimodal, bell-shaped is even more ideal, then a standard deviation and a mean work very well. In fact, we're going to see at the beginning of next class this empirical rule that allows us to really see how it works with a bell-shaped model. 5-number summary uses a median, uses the interquartile range to measure spread, which are more resistant and better to use when you have what kind of distributions? Strongly skewed distributions, not just slightly skewed. Slightly is okay to use a mean and standard deviation, but strongly skewed distributions, or if you have outliers. Strongly skewed distributions, or if outliers, because they will affect the mean and the standard deviation. The last bullet, and then a picture of the day. The last bullet is your calculator will often have lots of these numbers that can be summarized for you and calculated for you, but sometimes it even gives you more. Do you remember the first sample mean? X bar, that's the mean of a sample, that's called a statistic, and mu is the notation for a population mean. For standard deviation, we have the parallel of sigma versus S. Most of the time, I know on TI calculators, when you get your summary measures, sometimes on regular calculators with little buttons, they have a sigma button or an S button. The sigma is if you had a population of values and you had all those numbers put into your calculator. Then you want the population standard deviation, which is computed a little differently than the sample one. And you need to use sigma. But most of the time, the data that we have is from a sample. Most of the time, we're computing sample statistics and not true population values. So we're going to often pull off the S and not the sigma when that comes out from your calculator, so you know that difference. And then you get to see pictures of the day before you leave. I have 2 dogs. There's Lily and there's Molly. Lily is a 16-year-old beagle mix that can't hear, can't see, but she's still around. Molly is a lot of fun. She's kind of a cat dog. Keeps us busy with walks. I hope you have a good day. We'll see you on Thursday.